Let's get started. So I went ahead and adjusted the syllabus. So you'll see that things kind of moved backwards one day. Yes, so the midterm is now on the 3rd of November instead of the 11th, on the 1st. Were there any questions from last time, on Tuesday? You were all able to set up your development environment 1? All right, perfect. So what we'll do today is primarily go through ways to interact with a blockchain and extract information from the blockchain. There's a variety of tools that we'll be using. One is a Web3 API that directly connects to a node, and you're able to essentially query the blockchain that way. Then we'll briefly cover Ganache, which is essentially a tool that allows you to fork the blockchain at a certain block locally. So you can essentially submit transactions to it without submitting them to the actual chain. And then we'll go through ways to analyze blockchain data. So we talked about Etherscan. We'll go through the Etherscan API. And then we'll also look at some of the indexing services, in particular Dune and Luabase. All right. So basically, what the Web3 API does, and there's two versions of the Web3 API. There is a JavaScript version and a Python version. It allows you to read information from the blockchain. And we call that reading is free. And the way you do that is you connect either to a node that you run locally, or you connect to an infrastructure provider like Infura or Alchemy. Did you all set up Infura and Alchemy as well, or Alchemy? Alchemy? Okay, perfect. So then we're able to get the repo locally. Because probably what we want to do is just kind of walk through the examples and make sure that you all able to run the examples as well. Let's see here. Let me open it up. Okay, so read blockchain, we will do Polygon. And let me make this a little bigger so you see it better. And have you all worked in Visual Studio Code and Mark? Okay, that's fine. But you're able to run Jupyter notebooks? Okay. All right, so then we'll go through Jupyter Notebook. So the first one, of course, then kind of importing the libraries. And then one thing that I would recommend everybody to do when you're working with a blockchain is to split out your API keys and put those in the environment variable, and then make sure that the environment file is in gitignore. That way, there's never a risk of submitting your private keys or your API keys to GitHub accidentally. And then basically what we do here is we load the environment variables. Are you guys able to follow along? So I'm on 7 read blockchain state. Mark? No, I want to make sure that everybody's on the same page. So it's a Git repos that I set up. See, so the Git repo is right here. So if you go to the announcements, it's right there. Hey, Colin, I'm not able to hear you. Are you able to hear us? Let's see here. My mic here. Settings, internal mic, speaker. Yeah, it shows that he can't hear me.
I can hear you now. Sorry,
Okay.
it was on my side.
No worries. We all know Teams. All right. So basically, Colin, what we're just doing is we're pulling up the repo, making sure that everybody is able to follow along. So we're going through the first file, which is essentially reading blockchain state using the Web3 API. And there is the GitHub repo that is on the canvas in the announcement section. And I'm just waiting for everybody to have that so we can actually go through it together.
Sounds good.
Yeah, just clone it. And Colin, before you joined, what I was explaining is to put all your keys in the .environment file.
Yep.
And include that in Git ignore, so there's no risk of submitting your private key to GitHub.
Yep.
Many people do.
It's a very common thing, actually.
Sure, there's bots that just kind of search for those.
They're starting to actually put, at least on the enterprise versions of GitHub, there's blocking now, which is nice. So like you actually can't submit it, but.
Oh. If anybody needs help, let me know. No, I'll wait. You know, we're not a large class, so not a problem at all to wait. Seven, read blockchain state. And I'm just on the first cell. Because I want to kind of walk through the entire thing.
Christian, can I see your git ignore again, just really quick for the Python? Never mind. I'll find it on the repo.
You're good? Okay, perfect. All right, so then let's kind of walk through what we're able to do with the Web3 API. And let me just open up the browser here too. And so here's the documentation of Web3 API. And as you kind of go through it, it gives you essentially the APIs that allow you to get information about the node if you're connected to a node, as well as information about blocks, transactions, accounts, the chain ID that you're connected to. And so let's go through a few examples. So the first thing that you need to do is essentially connect to the node. And so we have our Polygon RPC endpoint, which is either Alchemy and Fiora node or local node. And there's a variety of ways you can connect to it. Here, I'm just doing an HTTP connection. And then after you execute that, then essentially the W3 is initialized. And then you can start interacting with the chain. And so w3.eth.block number gives you the latest block number, which is a large number for Polygon because they have a lot of blocks. So it's 34 million, blah, blah, blah. Do you guys all see that? Are you able to execute that as well? Great. Then you can also query the balance of a particular account. Now, one thing to keep in mind, okay, let me actually ask you, what does that give you when you execute get balance on a particular account?
It should be like the settled amount.
Settled amount, yes. Okay. Duke, you were saying? That's right. It's the native balance. So on Polygon, that would be Matic. On Ethereum, that would be Ethereum. So it has nothing to do with your ERC20 balance. Because in order to get the ERC20 balance, you actually have to read the smart contract state. So this only gives you the balance of the account in the native. Now, one thing that I want to point out here is what you see here on the address is that it is camel case, right? So some letters are capitalized and some are lowercase. Let me change it. And you actually get an error. And which one did I change? That I changed. Did I change this one? Okay, yeah. So I changed it here. Okay. And the reason for that is these addresses are checksummed. And basically that is a way to prevent typos in your address. And okay. Yeah, so it prevents typos in your address. And so that's just something to keep in mind when you copy addresses from Etherscan. Sometimes they're checksummed like this. Sometimes they're lowercase. And there's a function that the library provides to convert a lowercase into a checksum address. You can, when you query the balance like this, you essentially get the balance at the latest block. But you can also pass in the block number. So this is essentially the current block number minus 10,000. So now you get the balance 10,000 blocks ago. And so as you see here, the account has less matic now than it did 10,000 blocks ago. Mark, is it working for you now? Yeah, and here's essentially an example when, hey, if I lowercase it, then you get this error message because it's not checksum. And here's the function that allows you to checksum a lowercase address. This works now. Then there's also a whole bunch of helper functions that allow you to convert essentially the values that you get back. The values that you get back, from the get balance are in way. Oh, hang on. Uh-oh. Just a second, we got to reboot some stuff here. I think it's coming back up. Okay, we're back. Okay, so the balance that you get back is in way, which is essentially the value without any decimals. And so you can convert that into the full unit. So if you want to convert like a certain way to ether, then you can use Web3 from way, you get the balance, and then you specify the unit that you want to have back.
And matic is like, so really like matic is the same order of magnitude as ether, and that's why we specify ether here.
That's correct. It is, the Web3 API was created for Ethereum, and then all these blockchains appeared that were EVM compatible, that essentially worked with Ethereum. But then you have kind of these quirks, right? Where you say, hey, I want the ether, but really it is matic, right? So that's a little confusing. But I think all the native currencies and the other EVM compatible chains have kind of the same best decimals as Ether does. And so then it should not be an issue.
Opposed to just calling you to get account balance automatically. Guessing why you have that parameter there instead of just creating a separate API for it.
So you have the parameter, so you convert the way into Ether.
Oh, okay.
Because the get balance gives you way back, and if you just kind of want to convert that and have kind of the the right amount of matic in this particular case, then you have to pass on the Ether parameter. And the value doesn't change; it's just a different representation. Okay, so then the other thing is we talked about that there's two types of accounts on Ethereum or Polygon. Polygon is the chain that is that has matic, right? Mark, you had a question?
Making requests to your I just got in your error in terms of like it said I had like exceeded on retries connect and then so like the host is activating my connection now so I can't get your results.
Yeah, you can do HTTP. The other one that is let's see here. You can do IPC for a local node. And then a WebSocket. So if you have a WebSocket URL, but then you need to change the URL from HTTP to WS WebSocket. Okay, so then we talked about that there's two types of accounts on the blockchain. There is an EOA, which is an externally owned account. That's essentially the account that you all created with your wallet. And then there's contracts. And in order to differentiate whether you're dealing with a contract or not, you can query the address and basically say, give me the code. And if the code comes back empty, then you're dealing with an EOA. And if the code comes back non-empty, then you're dealing with a contract. So let's just kind of look up this address real quick. Polyscan, Polygon. Okay, so what you see on Etherscan is they tell you right here that you're dealing with an address. So they essentially do that right when they generate the index. If you were to go to a contract, you see contract up here. But that information does not exist on the blockchain per se. There's no flag saying, hey, this is an EOA or this is a contract. The way you find out about it is by getting the code. And so in this particular instance, we're getting the code. It is 0x, so essentially empty. And here is a contract, and let's pull that one up real quick. It's a contract. If you go to the contract tab, if you scroll all the way to the bottom, you see here's the contract code. And so you can get that through the Web3 API. And of course, this is all just the binary code. The source code that we see here on Etherscan does not exist on the blockchain. That is only exists on Etherscan. Okay, so then the other thing is contracts store data in storage slots, and we'll go into much more detail when we talk about solidity and development contracts. But the way to think about it is a contract is essentially a class, right? That consists of internal state. Hey, Colin, would you mind, or actually, I'm just going to turn down the volume a little bit. It consists of functions, and then it consists of state. And state are essentially a set of variables that the contract defines. And so, for instance, let's assume you have a contract student, right? So there's going to be a variable that says first name, variable last name, variable student ID, right? And so that's defined at the top of the contract, 3 variables that are essentially the state of the associated contract. And these variables are stored in storage slots that are sequential. So in the example that I given, first name, last name, student ID, in storage slot 0 would be the first name. In storage slot 1 would be the last name, and then storage slot 2 would be the student ID. And you're able to get the storage slots, what is stored at in the storage slot through the get storage at function, where you pass in the contract and the storage slot ID. And so let's take a look at this contract real quick. You can look at the code. The code hopefully is not too complex. We have all these functions, and there's an interface, abstract contract, strings, dun, 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 dun. Interface, interface, Another abstract contract. Abstract contract. Yeah, I picked a big one here. Okay, so there's the contract. Okay, so basically here you see the variables that are associated with its contract, right? So this is an ERC20 contract. Which one is it? Zcoin. And so there's a mapping. Mappings are a little bit different in terms of storage. We'll go through that. But then you have three variables here: total supply, name, and symbol. And so as you go through the storage slots, you're essentially able to access those variables. And you can analyze it in detail and then kind of figure out, hey, this variable maps to this storage slot. But often if you're approaching it from a security perspective, and you'll encounter this in the Ethernaut challenge, where maybe you need to figure out what a variable name or variable is currently set to, then you call the storage slot and just kind of iterate over the first 50 variables. One very interesting aspect is you see that these variables here are private, right? And private kind of implies nobody is allowed to read them.
But
That
in the blockchain, that's not true, right? Because it's all a single machine. So it just means private's really just talking about modification rights, not reading rights.
That's right. Did you guys hear him? Okay. So basically on the blockchain, private does not imply that you're not able to read them. It is more around how you can access it programmatically from other contracts. But since we are connecting through the RPC endpoint directly onto the blockchain, we have access to the entire state, and we're able to read whatever we want.
So it's live debugging of state.
That's right. And I'm sure you the get storage probably has a here. Let's just look it up on the API. Second. Storage at. So here, as you see, whoops, in the documentation, you're able to specify the block. Remember that a contract is essentially state. The current state, processing a transaction generates a new state, right? And so the state, the variable, let's assume, let's look at the contract again, and the name on block 1 may be set to foo, and the name on block 2 may be set to bar. And so by specifying the block here, you're essentially able to read the blockchain state at any block that you want. And if you look at a transaction, okay, let me go to Etherscan. So if you look at a transaction on Etherscan, you get a state tab, and it basically shows you the state before this transaction and the state after this transaction. So essentially what Etherscan is doing is this particular transaction was mined at block 228, right? And so after that is 228 and 227 is here. Now, I'm simplifying a little bit because, of course, there's transactions within the same block that could happen that modify the state within the same block. But generally, think of it like, hey, this is a state before the block got mined, and this is a state after the block got mined. So in the Ethernaut challenges, there may be challenges where they give you a contract and it may contain a secret that is not hard-coded. The secret is passed in dynamically when the contract is created, and you need to extract the secret in order to invoke a particular function. If you don't know the secret, the function will revert. If you know the secret, then you essentially solve the Ethernaut challenge. And so you may need to look at the get storage locations in order to find that secret. So the other way, so this is kind of raw, right? Like I'm just reading the storage slots raw, which isn't very readable. And so one way you can read contract state is by using the API. And the API is essentially the interface that is associated with the contract. It's a JSON that looks like this. So it contains all the functions that you can call, all the public variables, etc. And then you're able to load that JSON into an API variable. Then you create a contract where you specify the address along with the API. And then you're able to invoke functions on that contract. Oops.
Are you invoking the function, or you're just like navigating the data structure? You're basically saying this JSON is a contract, and I mean, is it making a call to the blockchain? I guess in that case, it is.
It is making a call to the blockchain. It's making a call to the RPC provider, but it is not submitting a transaction.
Understood. So it's you're saying this is the shape of this contract. Now let me establish a connection or define that contract as an object I'm going to interact with, and then I start to go in and like basically do like gets from any of the individual attributes directly.
That's right. And if we go to Polyscan, so let's pull up that contract. It is essentially equivalent to the read contract tab, getting the decimals here. So whatever is exposed here, let me just go to decimal. So here it is defined in the API, and as a result, I'm able to call it. Let me see how that is. Decimals, right? So it's actually a function, a public view function. That modifier basically says, hey, it's a function that you can invoke without a transaction. And so that's what we're calling. The functions, if we go back here to the read contract, balance off is a function that takes in a parameter, and all it's doing again is reading state. And so you're able to say the contract that we just defined with the API functions balance of, and then we pass in the account for which we want the balance. And then we just kind of divide this by the decimal so it's more readable. Okay. Next, you can also use the Web3 API to get transactions. So let's look at one transaction in Etherscan. So here's the transaction. It was from 165B to a particular contract, the Z token. You're able to get information about the gas price, 14-way. And then you see down here that the transfer function was invoked from this account, this particular amount, right? So that's what we see on Etherscan. And so now let's take a look at what we see when we pull this up through the Web3 API. And so you get the hash, you get the block number, you get the from, gas price, etc. And then you get the input here. Oops. The input here, which is essentially the input data that gets passed along with the transaction, which is equivalent to this string right here. This first 4 bytes is essentially the function selector. So basically, when you send a transaction, you basically tell the contract, hey, I want to invoke the transfer function. And there's a huge switch statement in the contract that says, hey, if the hex code is this, then jump to the transfer function. If this is the hex code, then it jumps to the allow function, etc. And so this particular function selector, this hash refers to the transfer function. And then basically it has 230 byte fields, which correspond to the 2 parameters of the transfer function. And so let me go back to the default view, which is essentially the to address and the amount. So this says transfer, to, and the amount. And again, on Etherscan, much more readable than here, right? Because basically you just get this input field and you better figure out how to parse that. Also contains the nonce. Have we talked about the nonce?
It's the thing that made the transaction work. Like it's the for the hash to work correctly, that's what had to be added to it in order for it to solve correctly.
Okay, that is correct in context of mining, but there's actually 2 nonces. So there's the nonce for mining, which you're talking about, Colin, which is what the miners have to add in order to generate the hash. So it starts with zeros. The nonce on a transaction is actually a nonce that is associated with the account.
Oh, is this the sequence? It's the sequence number?
It's the sequence number. And so basically, when you create a new account, then your nonce is 0. You submit a transaction, your nonce gets incremented with every transaction. And what that does, it just kind of orders your transactions. If you submit many transactions at the same time, right, the transactions will have a nonce 1, 2, 3, 4, and the miners then essentially will pick it up in order. Yes. It basically tells you not necessarily information about the age, but rather how active that address is or has been. And so this particular address, 257,000, that is a lot of transactions. So let's take a look at this. 328,000 transactions. So it's probably an exchange or a mixer or a bridge. I mean, could be anything.
They have the same nuns within a block. What you choose?
Well, the miner will probably choose the one that has a higher fee. If they're the same, I think it's non-deterministic. I think they just pick one. And sometimes you can even get stuck where, and you'll see that with programming. It's actually something to talk about. So if you when you submit a transaction, and we'll go through that here in a second, you have to specify your nonce. And if your nonce is off, let's assume your account nonce is 4 and you submitted transactions with a nonce 7, it will not get picked up by the miner because they're like, hey, I'm expecting nonce 5. And so that's just something to keep in mind as you are submitting transactions. It's best to read the nonce of the account and just increment it by 1. And then it's always in sync. Yes. 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 Yeah, and we kind of did that right here, right? We basically queried the transaction and said on this transaction, what was the nonce? And so you could look at all the transactions made by a particular account, latest transaction, you get the latest nonce. Now, I don't know whether you can query it in a way, give me the latest nonce for that particular account. I know you can do that for your own account. Well, we'll go through it when we create a transaction. Then there's some signature information and the chain ID. And that's essentially all you get from when you call get transaction. And so it's not a whole bunch of information. So if you think about this, the state tab, right? Like how did the state change? That's not part of the transaction. Where is that actually located?
It's in the block, right?
It's in the block. So here's the block. And where is it?
It had the transactions up above, the third thing, 54 transactions.
Yeah, there's 54 transactions, but I was looking at something else. So let me show you on Etherscan. And again, what you'll see here is slightly different. Basically, it's in the state root, right? The state root is the root hash of the state Merkle tree. And so that hash will be modified once a smart contract modifies the state of the blockchain, right? And somewhere in the tree, the state was modified. Okay, so then we have the input. Okay, so the input I already explained. So this is the function selector. Now the function selector is a hash. And the way to calculate the hash of the function selector is by taking the Ketchak hash, which is the SHA-3 of the function signature. So here is the function signature, is the transfer, which is essentially the name, and then the types of the parameters without any spaces. That generates a hash, and we take the, the first 1, 2, 3, 4 bytes. So I take the transfer, that's 2 parameters, address and UINT 256. We hash that, which let me just give you the whole hash. Right, long hash. And then we take the 4 first byte, and that is the function selector. And that's how you can convert a name or a function to the hash. And that's it. I mean, that's essentially what the compiler does. And if we go back to Etherscan, let's look at a block. Let's look at the transactions. What you see here in the method is it essentially converts the function hash that is contained in the transaction to the function name, right? So here we have a transfer, and if we go into the input data, whoops, oh, this is native transfer, sorry. Let's see here. I think this is a non-native transfer. Nope. Well, I had it over here. There, right? So basically, this is the data that gets passed in. We know now that it is the transfer function. And then what Etherscan actually does when you look at the block or look at the transaction, it populates that field, right? But let's see whether I find one. Explorer. I think I think the likelihood of collisions is very low, and so they just kind of for space optimization. I wanted to show you is a function invocation where Etherscan is essentially failing. There we go. Okay. So here you see that essentially Etherscan doesn't know the method, right? So it doesn't convert the function name to an actual, the function hash to a name. And the reason for that is you cannot convert a hash back to a name, right? You can only convert a name to a hash. And so what Etherscan has done is probably analyzed all smart contracts, maybe some permutation, and then basically generated a gigantic rainbow table of function names to hashes. That's right. So you'll see common function names, and whenever you use something that is uncommon and you don't upload the code to Etherscan, then Etherscan is like, I don't know what the function is called. But it is very interesting from an exploit perspective. If you see these, well, that kind of indicates to you it's an uncommon function, right? That's right. It could also mean that they didn't upload the code to Etherscan. I would assume that Etherscan will parse all the code, parse the function signatures, and then generate the mapping dynamically. Something that we could try if we upload a contract, if we deploy a contract and then upload the source code, see whether it comes up with a mapping. So as I say, this is a transfer function to parameters for bytes. And so you're able to then kind of parse this, of course, the input field, right? So you can get the function hash, which is in the first 4 bytes. Then the next 32 bytes is the address, next 32 bytes is the value, right? Now, depending on the parameter size, those offsets may be different, right? Like if you have, let's say, an address, which is 32 bytes, and then you have, let's say, 2 parameters that are 128 each, so 16 bytes, it may get packed.
Okay, and we already looked at the transaction on Etherscan. All right. Next up, let's look at writing to the blockchain state. Now, when you write to the blockchain, you are submitting a transaction that you need to sign with your private key. You need to pay transaction fees, right? And then your transaction gets submitted to the mempool and then gets mined. So let's go through that real quick. All right. So you can have your imports, you connect to the chain. And then this is important. Now, here you're essentially reading your private key that you have exported from MetaMask. Did you all do that already? That's right. It's a long hex string that then gets essentially read, and then it creates your account variable. Your account variable then has a public address. So this is my account, right? You can look that up on Polyscan. You can see it currently has, you know, $15 worth of Matic. So 18 Matic. Which we can get the balance. And then now we want to send 0.1 Matic to this address. So let's pull that up on Polygon again as well. So this one has 1.3 Matic, right? And this one has 18.69 Matic. So we get the balance here, 1.3. Remember, this is in way, right? So it's a large number. Then what we'll do here is we get the max priority fee, which is essentially the gas cost, right? Because again, we will have to pay for gas. And so we will, in the transaction, specify how much we want to pay for gas. And here is actually the function that gives you the number, the nonce for that particular account. And then we will create a transaction, and a transaction is essentially just a JSON object with the fields that you would expect. It's basically the nonce, who you're sending the transaction to. The value here is the value that we want to transfer. So if we're not invoking a smart contract, but rather just want to send Matic to another account, then this one is an EOA, and then we specify a value, and that will lead essentially to just a transfer. And so it's 0.1 Matic. This is an important field, chain ID. And let me explain to you why that is important. So the chain ID 137 is Polygon. Chain ID 1 is Ethereum. And so let's assume we don't have the chain ID. What would that allow me to do?
You could potentially cross-contaminate. Well, I think you would just lose. You would lose the token potentially, right? Or you would send it to the wrong network. I guess you would send it to the wrong network.
Yep, that's right.
Does that also create double spend? Because if I can send it to the networks, I could send. No, it still goes out, so that shouldn't happen.
Yeah, hang on, Colin. Duke was talking. Duke. Yes. So we're connecting to the Polygon RPC provider. The RPC provider may say, hey, you do have to specify the chain ID and reject the transaction if you don't specify it. Colin, you were onto something with double spend. Let's assume they don't check the chain ID. I am now sending a transaction basically saying transfer 0.1 Ether from this account to another account. That transaction is signed by with my private key. And so I could take the same transaction and replay it on another chain. So let's assume I sign this on Polygon, it transfers 0.1 Matic. I could take the same transaction and just submit it. I don't no longer have the key, right? Like I can read the transaction on Polygon because it's public. I can then submit it to the Ethereum chain, and it would transfer 0.1 Ether to the account.
And because this is included in the hash, it makes it so that the signed transaction content it prevents replayability entirely.
Exactly. Now, a funny story, when Ethereum moved to proof of stake, there was the proof of work Ethereum chain that continued. They created a new chain ID, but they forgot to check the chain ID when accepting transactions in their code. And so that allowed somebody to execute replay attacks. Oops. So chain ID important. And then the gas. So this is the amount of gas that we are essentially making available for the transaction. If the transaction uses less gas, you get that refunded. Then here's the gas price and the max priority fee. And then we essentially sign the transaction with our private key. And then we send the raw transaction on chain. And so let's do that. So now that is submitted on chain. Let's look at it.
Should we submit it as well, or do we not need to go fund this wallet heavily?
Yeah, Duke is watching out. He's changing the send value to another account. But thank you, Colin. I think if you want to donate some Matic to me,
I just said some.
I wish there would be more students in this class. All right, so here you see it is mined successfully from 0.1 Matic. And if we look at the two accounts, you see that the state has changed accordingly. So that's how you write a transaction on chain. And you can then wait for the transaction receipt. Oops. And then you get essentially the information on this particular transaction. And now we can look at the balance, and of course it has changed. Okay, so that was a simple transfer. And so let's take a 5-minute break, and then we'll go into contract transactions. So let's be back here 7:10. All right. Okay, well, let's get started again. Okay, so that was a simple transfer. So we send a transaction to another EOA. We want to interact with a contract, very similar. Okay, so if we want to interact with a contract, very similar, but what we need to do is specify the API, because now we are going to invoke a function on the contract. So just similar to how we read the state earlier on a contract, we just do it right. And so we have the USDC, which is a stable coin. Here's the API, which is this long JSON. It's an ERC20 token. And so you will have a function on there like transfer and approve. And so we load the JSON, we instantiate the contract, and then essentially we call function approve. We pass in the the address that we want to approve, and then the amount that we want to approve. We built the transaction in a very similar way. We specify the gas, the chain ID, the gas fees, the from address, the nonce. And what that will do is essentially it will take this section right here, which is the approve to and the amount, and we'll convert that under the hood into the input data that then essentially gets passed to the transaction. We sign the transaction with our private key, we send it, and then we wait for the receipt. So now that got submitted. Here's the transaction hash. So let's look at that in the Explorer. It's probably still, oh no, it's already mined. Okay, so here's the from address. We are interacting with USDC coin. Again, Etherscan does a lot of work for us. It actually tells us, hey, we approved USDC on this particular account. But if we go into the more field, into the input data, you essentially see the approve function, the spender, and the amount, right? So here's our one, and here's our spender account, which we had specified over here, the to address. Okay? So that's one way you can invoke a smart contract. The other way is you can invoke a raw call, because at times you don't have the API of the contract, right? And so what do you do in those cases? You essentially do a raw call. And what you first do is you create the function selector by creating the, well, by calculating the hash, taking the first 4 bytes of the function that you want to invoke, right? So this is the function selector for approve. We convert that into hex bytes, and then we essentially append the address. We got to pad it. Now this is probably not very elegant. There's probably some helper functions that allow you to do that more easily. But basically all that's happening right here is to encode the 2 parameters, right? And that's now stored in value. It is the approve function plus the 2 parameters. And then we create a raw transaction, similar fields, but the big difference is the data field, right? So now in the data field is essentially the input data that we're going to pass along. And then we sign that transaction, submit it on chain, and whoops. Oh, I didn't execute this. And so there's the transaction hash. So let's look that one up. There we go. Ah. So here, let's look at the parameters that got passed in. So I called approve. I passed in the spender, and then actually I passed in 0, meaning I'm actually revoking this account being able to spend my USDC tokens. And that's why it says revoked here instead of approved. Any questions? Yeah, we're still calling approve, but basically, in order to revoke, you just pass in 0 as the amount. And then basically, it basically says you're approved for 0. So that's a little bit of a quirk in terms of how the approval works. Okay. Yes and no. You, as I mentioned earlier, when you look at the contract code, let me show you. So here's the contract. And let's look at the contract code. And we're going to switch to opcodes. Essentially, what you will see at the beginning of the function is a gigantic switch statement. And you continue to see these push 4-byte codes. And if you go down this list, these are essentially all the function selectors of that smart contract. So further down, you'll eventually find the approve one. And so theoretically, what you could do is if you don't have an ABI, you can switch to the opcodes. You basically parse the opcodes, extract all the 4 bytes, and then you could invoke those functions. Now, one challenge that you will have there is you don't know what parameters are being passed in. Because recall that the function signature basically consists of the name and then the parameters. And so that then becomes a little bit complicated. So if you have the approve function selector, you still need to know that you need to pass in an address and an int, right? But if it's a function that doesn't take any parameters, then you're set. All right. So then next up, let's look at what if you want to write to an older block or act as if you had a private key. You cannot do that on the blockchain, right? Because the miners will only mine new blocks from the latest block. And of course, you don't have all the private keys. And so there's a tool called Ganache that essentially allows you to fork the chain at any block you specify locally. It then gives you a local RPC endpoint, and then you can connect to that endpoint and do whatever you want. And so let's take a look.
Essentially, all the functionality is if there was a brand new function.
That's right. And so in order to do that, you first need to start Ganache. And so here is how we can start it on Polygon. So essentially what it does, it says, hey, RPC endpoint, I want to fork at this particular block. And then basically it gives you a new URL which is the local endpoint that you just forked. And now you can just connect to that just like we did just now. So here we have our Ganache one. And as you see here, we're now connecting to an RPC endpoint that is the local one. And now you get the block, which is the, as you said, the next block essentially, right? It's 44. We forked at 43, and now we're at block 44. The thing that Ganache allows you to do, it gives you a whole bunch of private keys when it instantiates the chain. It's already funded, and you're able to submit transactions as any other account as well. So if you, it becomes very interesting when you're dealing with an exploit. So think of an attacker deploys an attacker smart contract that will steal millions of dollars. You can fork it at that chain, and then you can invoke that smart contract as the attacker and kind of simulate the attack locally. Yeah, you could basically just kind of, so an attacker usually does, deploys a smart contract on block 1, and then invokes that smart contract on block 3, let's say. That's 2 block difference. That's 30 seconds on Ethereum approximately. You can fork it when they deploy it, and then just start invoking it, and then basically see, well, are there a lot of tokens being transferred? And if that's the case, then you conclude, oh, this is actually an attacker smart contract before the actual exploit transaction gets mined. Any questions?
Verify that they're back or something or whatever. You have to maybe be able to process that for each and every transaction to your contract. Because you have to like have some assumption that this looks kind of suspect, right?
Yeah. And on the Forta network, there is a detection bot deployed that basically monitors any smart contract deployment and then tries to invoke that smart contract and then assesses, are there large amounts of tokens being transferred? It's an attack simulation bot. But you're right, like if a smart contract gets deployed, with every single transaction, that probably would be too expensive, but new smart contract deployment isn't that frequent really. All right, so now you know how to read and even write to the blockchain state. So now let's look at a few questions here. How would you get all transfers of USDC? So USDC is a ERC20 contract, and I'm interested, I want to get a list of all the transactions that contain transfers of USDC. Yep, the transfer. All of them.
For the transactions, put it down using the transfer bytes.
Okay.
Then we pass the first 10 characters to get the hash. The transfer, we map them with the domain.
That's exactly right. So you basically get all the transactions from all the blocks. You analyze each and every one. You look at the to address, whether it's a to address to the USDC contract. And then, as Duke said, you look at the input data, look at the first 4 bytes to see whether the transfer function is invoked. That's how you would get all transfers of USDC. There's 35 million blocks on Polygon right now with hundreds of transactions each, it would take you forever to do that. So it's not really a feasible approach. How would you get all contract creations?
You would look at the zero address for all of the transactions to the zero address.
Right. The zero address is a special address that gets invoked when you deploy a contract. Again, you would have to go through all the transactions, every single block, in order to find that. How would you get all transactions for a given account?
Same thing, loop through every block looking for that, either in the from or the to.
Right. That is just way too slow. And so as a result, there's all these service providers that make that easier for you. One of them is Etherscan. Etherscan, as we discussed, is more of a UI tool, but they also have an API that allows you to get, where is it? That allows you to get this data in a more convenient way. And so, for instance, contracts. You can get the API for the contract, or actually, let's see, transactions. There's, nope, must be in accounts. Get a list of normal transactions by address. So that function, you basically pass in the address, and then it will give you all the transactions associated with that address, which on my account that we used here, right, we have 9 transactions. So it will give you those 9 transactions. If you were to use the Web3 API, you would have to analyze 35 million blocks to get that information. And so let's look at how that looks like. So what you will need is the API key. So if you go to Etherscan, if you sign in, I'm going to do that right now. But then there's a section that gives you an API key. So which one am I going to invoke? Yeah, so essentially what I'm invoking here is the API call that gives me all the transaction for a particular account. So let's go back to the documentation. So basically I'm saying, give me all the transactions for that particular address. There's the information that you need to pass in. And then in the response, why is it not allowing me to click that? I don't know. But in the response, essentially here are the fields that you get back. Block, timestamp, hash, nonce, index, to, from, value, gas, input, contract, receipt status, errors, etc. And so you invoke that, and then boom, you get all the transactions for that particular account with all the information you essentially see here. Okay. So that's one way to get more, get certain data faster. Any questions on that? Yep. So Etherscan, it's free for a low number of requests, and if you really hammer the API, then they will charge you. And there's some rate limiting as well, like in terms of how many requests you're able to make a second. All right. Okay, so now let's assume you have Web3 API and you have Etherscan. And so again, let me ask the question, how would you get all transfer events of USDC?
For the new events, we need to listen to those events, but for the past ones.
The Etherscan API still does not allow you to do that. I mean, you're able to look at an account and see the transactions, but holistically, you're still not able to do that. And so that's where indexed databases come in. And there is Lua base, which is kind of a new service on the block that allows you to access essentially blockchain data. Hang on. Or not. Okay. So here you see a few queries. So let's get those to Lua base. Oh, hang on. Oh.
And so we need to go sign up for like an Etherscan API key and a Lua base API key and all that kind of stuff.
Yeah, and all these services are free.
Yep.
Okay, so here we have our 3 queries. So essentially, what Lua base does, it takes all the transactions that were ever mined, and of course it updates as transactions comes in, and sticks that into a big table and exposes a SQL interface on top of it. And so that makes it super convenient. So if I'm interested in, hey, give me all the transaction from this particular account, we write a SQL query that does that. The from Polygon transactions where the from address is boom, right? It is fairly quick, takes a few seconds, because again, you have to keep in mind that it is essentially querying 35 million blocks with hundreds of transactions each. Usually it does not take that long because those tables are indexed. Yeah, not sure why it's taken so long, but you can trust me that results will show. Now with SQL, of course, you can do more stuff, right? You can do joins, you can do aggregates, and so you can also do, let me interrupt this. Maybe the next one is going to be quicker. So you can say, hey, give me the count of all the transactions for that particular account. And it's not working. Right. I'm not gonna waste your time. But now, Duke, if you want to get all USDC transactions, transfer events, you're able to issue one query to get you that, right? You basically go to all the transactions. You say, hey, if the input is like the transfer function selector, and then probably we want to put the, so let's do that real quick. Got the USDC address. To lowercase that. Oops. Switching so much. There you go. Now that gives you, and that actually returned fairly quickly. So that gives you all the transfer transactions. Yeah, yeah, that's right. All the transfer transactions that involve USDC. I was pausing a minute here because the to address, there's two to addresses, right? There's the, let's pull up a transaction and I'll show you what I mean. So this is a transaction. It's it's approval. Never mind. But change the hash. There's the to address, which is the contract, right? That's right. If you have a transfer function, you say transfer to somebody, right? A particular amount. So it's going to say something like transfer to, and so there's two to addresses. The first one is the to address to the contract that I'm invoking, and then the to address and the transfer is encoded in the input data field. But here in the query, we're not parsing out the to address from the transfer event, but rather just querying the to address of where was the transaction sent to.
Like adding to USDC or using like adding the transfer USDC.
That's right. Matic is a native, and so Matic in this particular transaction is merely used to pay the transaction fee. But what you're really invoking is, hey, take in the USDC contract, there's my balance is 100. Take 100, like 10 off my balance and send it to somebody else. The nice thing about Lua Base, it also has an API that essentially allows you to issue the same queries in Python. And so again, what you need here is an API key from Lua Base. And so what am I doing here? Here I'm extracting essentially the Ethereum tags from a set of addresses. So here I have a whole bunch of addresses. One thing to keep in mind that you need to lowercase them for Lua Base. And so then I'm issuing, whoops. Base API key. Okay. Never mind. So I'm not able to show you that right now, but because I don't have the API key configured. Let's see. Okay, I will fix that and submit the fix to the repo. But yeah, the nice thing is that you're able to access it to. Oh, dang it! Did I touch this again? There's just this little button here.
It works great. It's still working great for me.
Yeah, thanks, Colin. There's just that one button that is just right at knee height. So great that you're able to do that through Python, because now basically what you have in Python is essentially everything available, right? You have Web3 API, you have Lua base, so you can theoretically say, give me all the contracts from Lua base, and then for every contract you get the code from blockchain. You could then go to Etherscan, get the source code, right? And so you have a lot of information available to do a lot of analysis. And for the assignment that we'll discuss next week, you will have to use all these tools to answer the questions that I'm asking. We'll discuss those next Tuesday. Okay, we're back.
So between now and Tuesday, good to get the rest of the environment set up done, but then also get API keys for Lua-based Dune and Etherscan.
Yes, yes, exactly.
Does Dune have an API, or is Dune just web interface?
Yes, Dune does not have an API, and that's exactly what sucks about it. It essentially is, and we can go through this here real quick. So Dune is really a query and dashboarding platform. And I do have an account here. And what that allows you to do, if you have an account, you're able to download the result as a CSV through the interface here. If you just sign up for it, you can still issue the same queries, you can still create dashboards, but you're not able to download any data. Now, Dune, so one thing with Lua base, if you look at, is it bugs? I think it's not showing. Yeah, their interface changes frequently, and I think their button is missing. So there's usually a button that says Explore or Schema Browser. There it is. They changed it. And so here we have Ethereum, and then here are essentially the tables that are exposed in Lua base, and they are very high level. So you have a table transactions. You have a table token transfers. What Lua based, what Dune does, it has much more fine-grained tables. So let's assume I am Aave, which is a collateralized lending protocol, and I'm interested in somebody calling the borrow function. And so what Dune does, it parses out all the relevant information associated with the borrow function and makes that available in a table. And so the data is more indexed as it is on Lua base. On Lua base, you can still kind of get that information, but you would have to parse essentially the input field for the function selector and the various parameters, right? And kind of parse that out. Lua base, pretty much everything is already indexed. So that makes it very convenient if you're interested to deep dive into a particular protocol in more detail. Let's look at a few, or let's look at one query. Oh, that's already the query. Okay. So basically here, what we're doing is we're selecting from ERC20 events approval. So these are the emitted events, right? So it's not only parsing transactions, but also events that get emitted. Again, keep in mind, events can lie, depending on who emits them. And so that, of course, is already a much smaller table than the entire transaction table. So that makes it quicker, for instance. So we're looking at all the ERC 20 approvals. We're parsing the block time into a day, and then we're counting essentially the unique transaction hashes as the number of approvals. We're looking at a time period of the last 2 months, and then we're looking at the wrapped Ether token. So basically what that query does, it gives you the number of approvals for the wrapped Ether token over the last 60 days. And so there's about 5,000 or so approvals, 4,000 or 5,000 approvals every day. And then what you're able to do is you can create a, oops, hang on. Usually I don't do the dashboarding. Add to dashboard, new dashboard. Actually, it shows the dashboard right away. Hang on, new line chart. Oh, there we got a line chart, and then there's a new visualization. So there you go. You go to new visualization, and then you can create a chart out of the data and manipulate it however you like. And so Dune is really more of a dashboarding platform. And if you go to the main site, one thing that Dune also has done is whenever you create a query or when you create a dashboard, it is public by default. And so a lot of people create dashboards. And here, discover, so here are all the dashboards. Let's see, maybe there's something, Bored Apes here. Bored Ape Yacht Club data. Here it gives you the OpenSea floor price of a Bored Ape. Here's the corresponding table. Sales per day. So as you can see, it has quite dropped off compared to the NFT mania back in April. Volume per day, I'm not sure what that is. Top sales. And so there's all sorts of dashboards that the community creates, and as I say, they tend to be public by default. So there's a lot you can do with Dune, but it is it's actually impossible to programmatically interact with Dune. So if you want to analyze some data and do that from a Jupyter notebook, Dune does not allow you to do that. For that, you rather want to use Lua Base. Questions? All right. Well, that's all I had for today. So for next time, install the dev environment 2. So you have essentially dev environment 1, which is the Web3 API and the Jupyter notebook, and you're able to do all these queries. As Colin said, get the API keys and make sure that you're able to run these. You will need these for the first graded assignment. Then proceed to install development environment 2. This is really more around smart contract development. And so it installs Brownie, which is the Python-based development environment and testing framework. And if you have any questions, feel free to reach out on this discussion forum or just email me or Telegram
Christian, do you use any in particular extensions in VS Code? Like there's one for, I think there's one for Solidity or blah, 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 blah.
Yep, I use the one for Solidity, and I think that's about it.
And then the Jupyter one you're already using to just get the Jupyter environment working. Yeah, okay.
That's right.
Okay, cool.
Okay, right on.
Thanks for the dial in. I'm gonna go
Yeah.
make sure my kids are asleep now.
Yeah, thanks for joining. Have a good
Yep.
one.
Bye.